When we talk about sorting data, you've probably heard there's this wall, a theoretical speed limit that seems totally unbreakable. But what if I told you there's a way to get around that wall? Not by sorting faster, but by sorting, well, smarter. Let's dive in.
Right. So this is the big question. We all know about the classic algorithms, quick sort, merge sort, and they're famous for that awesome O of n log n efficiency. So you got to wonder, is that it? Have we peaked? Is that the absolute best that humanity can do?
And for a huge family of sorting algorithms, the answer is kinda yeah. N log n really is the finish line. And we're not talking about a hardware limitation here. This is a hard mathematical boundary. But, and this is the key to everything, it only applies if you're playing by one specific rule.
And that big rule? It's all about comparison. See, a comparison sort is any algorithm that works by picking up two elements and asking a super simple question. Hey, is this one bigger than that one? The entire sorted list is built step by step from the answers to those little questions.
And here's the thing. For any algorithm that only uses those comparisons, there's a proven lower bound. In the worst case, it's going to take you at least n log n comparisons to guarantee you have a sorted list. It's kind of like the speed of light for sorting. You just can't go faster. So, if that's the law, how do we break it?
Well, you know the saying, if you can't break the rules, you find a new game. So what if we could sort our data without ever comparing one element to another? Does that even sound possible? It feels a little like magic, but really it's just about using information that those other sorts completely throw away.
You bet. And this is where we totally flip the script. On one side, you've got the comparison sorts, always asking greater than, less than. But with counting sort, we just stop asking. Instead of comparing elements to each other, we use the actual values of the elements themselves to figure out exactly where they're supposed to go. It's a whole different way of thinking. So, how in the world does this work? It's actually pretty brilliant. First, we just make a quick pass through our list and count how many times each number appears. So 3 5s, 2 7s, you get the idea. Then, we use those counts to figure out the exact final position for every single element. And finally, we just loop through our original list one more time and place everything where it belongs in a new sorted array. Boom, done. Not a single comparison between elements.
Okay, hold on. That seems way too good to be true. There has to be a catch, right? I mean, if this thing runs in linear time, why aren't we using it for absolutely everything? And yeah, there is a catch. This little magic trick only works if your data is integers and they fall within a pretty small known range. You can't sort a bunch of names this way or giant numbers because you need a ridiculously huge counter array.
That's exactly right. Counting sort is incredibly powerful, but it's a specialist. But what if we could take that specialized power and apply it in a really clever way? Well, that's where radix sort comes onto the scene. It takes the main idea of counting sort and just applies it piece by piece, or, well, digit by digit. Now, radix sort can feel a little backwards at first, because it works from right to left. Let's look at this list of codes. The first thing we do is completely ignore the letters. We just sort the whole list based on that last character. The 2s, the 3s, the 5s, and so on. The result looks like a jumbled mess, but trust me, this is a crucial first step.
Okay, so now we take that partially sorted list from the last step and we sort it again. But this time, we sort it by the first character. And just like that, poof, the final list is perfectly sorted. But wait a second. How did it know to keep F2 before F6? They both start with F. That's the real secret sauce, and it comes down to one single, super important property.
Exactly. How does the algorithm remember the order from the previous step? And more importantly, how does this work with real-world data? I mean, if you're sorting records in a database, you're not just sorting keys. You've got all that other satellite data attached to them. You have to make sure the right name stays with the right employee ID, right?
The secret ingredient that makes this all possible is a property called stability. A stable sort is one that promises to maintain the original relative order of items that have the same key. So, if F2 came before F6 in our list, a stable sort on the letter F guarantees that F2 will still come before F6 in the output. It respects the existing order.
And this is the perfect way to think about it, especially if you've ever worked with a spreadsheet or a database. Imagine you sort a table by student grades, but only the numbers in the grade column actually move. The student names just stay where they were. You'd have instant chaos, right? The wrong grades would be next to the wrong names. You need the whole row to move together. That's what stability gives you. And that is the big reveal. This is the moment it all clicks together. Radix sort isn't just one algorithm. It's a process that uses another sorting algorithm under the hood. And that algorithm has to be stable. Guess what? Counting sort is stable. So when radix sort sorts by the second digit, the stability of counting sort perfectly preserves the order we just created from the first digit. It's that property, pass after pass, that gets the whole thing right.
So you see, that O of n log n speed limit, it's totally real, but only for comparison sorts. If we understand the kind of data we're working with, we can switch to a whole different strategy, avoid comparisons entirely, and achieve amazing linear time speed. We didn't break the law of physics, we just found a different rule book to play by. If this explainer unlocked a new way of thinking about algorithms for you, do me a favor and help other people find it by hitting that like button and subscribing for more.
And that brings us to one last thing to think about. We just saw how a specialized algorithm can absolutely crush a general-purpose one in the right situation. So that begs a bigger question. When could an algorithm that looks slower on paper, maybe even an n-squared algorithm, actually be the fastest choice for a real-world problem? Something to chew on.